Okay, we got a bit of a fun question today, at least as far as a brain bender to deal with. Um, you remember this diagram because we've seen it a couple of times in this book. Parallel plate capacitor, surface charge negative sigma on the top, surface charge positive sigma on the bottom. Length L, width W, all that kind of stuff. But now you see we're moving them to the left. Okay, so keep this in mind or pause the video and come back to it when you need to. But this is what's going to be discussed today. So let's dive in. So our statement reads, why can't the electric field in the diagram have a Z component? After all, the magnetic field does. Okay, well, solution then. One way to see it is to look at the general formula for E in the 𝘐𝘯𝘵𝘥𝘶𝘤𝘵𝘪𝘰 equation. I can never say that right. But that was the generalized fields for the moving charges, moving distributions that dealt with the retardant potentials, the retardant times in the integral formulation. That being said, for a uniform infinite plane of charge moving at constant velocity in a plane, we have J dot equals 0 and rho dot equals 0. While rho, or rather sigma in this case, is independent of t, so retardation does nothing. Therefore, the field is exactly the same as it would be for a plane at rest, except for that sigma itself is altered by Lorentz contraction. Okay, so let's dive in a little more on this. A more elegant argument exploits the fact that E is a vector, whereas B is a pseudo-vector. Now let's rewind. Why a pseudo-vector? Well, that's because B was the cross product, if you recall. And the cross products tell us that although we have vector characteristics, they weren't actual vector quantities. They just resulted in a vector, and because the resultant is a vector product, it's technically a pseudo-vector. It wasn't a measured vector. Although you could always debate that, but the mathematics is that because of this cross product, same thing with torque being a pseudo-vector, the B field is a pseudo-vector simply due to the cross product. So this means that any given component changes sign if the configuration is reflected in a plane perpendicular to direction. But in a diagram, if we reflect the xy plane, the configuration is unaltered. So the Z component of E would have to stay the same. Therefore, it must in fact be 0. By contrast, if we reflect in a plane perpendicular to the y direction, the charges trade places, so it would be perfectly appropriate that the y component of E should reverse its sign. So again, we have to go back to kind of these definitions and see how and why of things. The cross product being a pseudo-vector means that we are the resultant of two other vectors, and that's where the sign change comes in and things of that nature. So be aware that there's always several routes to the same answer, and that's what makes physics fun, but it can also make things confusing. That being said, go ahead and take a look at it yourself. Let me know what you think. Yeah, let's have a conversation. This stuff's really cool. Later.